Good morning, friends. Welcome to the lecture of lattice theory. This was the fourth lecture we are conducting today. We will just have a look on what we have taken in the last lecture. In the last lecture, we have studied the distributive inequalities in lattice theory. Actually, in other group theory and all, we have seen these are the strict equalities. But in lattice theory, this distributive are inequality. Distributive property is given by the inequality. We have seen the proof of how this distributive inequality is proved. Also, we have seen the principle of duality concept, then product of lattices, and by a theorem also we have proved that the product of two lattices is lattice. Also, we have seen the examples that how to write or how to draw the Hasse diagram of the product of the lattice. Okay, now let us come to today's lecture. In today's lecture, we are going to study homomorphism property. Okay, homomorphism is known to us. Okay, with respect to any other aspect, can anyone tell me what is homomorphism? Suppose with respect to group, what is homomorphism? A mapping is said to be homomorphism if, yes, can anyone answer? Homomorphism?
A function defined from G to G dash.
Hmm?
Operations, multiplication and any other operation in G dash.
Hmm?
F of xy, x into y is defined as x, f of x, a function of G dash into f of y.
Good. That is, it is operation preserving rather.
Yes, ma'am.
Correct? Now, in short, if I want to take. Now here in lattice theory, we have studied two operations. Which are the two operations we have studied? Join, which is least upper bound, meet, which is greatest lower bound. Therefore, we are going to define the homomorphisms with respect to the two. Also, we are going to define the homomorphism with respect to order. Okay, what is the order? Comparability relation we have discussed already. Okay, so let me write the definition. Let L and M be lattices are mapping F from L to M if. Now we are writing the conditions along with the homomorphisms. First, it is joint homomorphism. It is joint homomorphism. What you say when it will be a joint homomorphism? If f of x join y is equal to f of x join f of y. Okay, therefore which operation is preserved here? Join operation is preserved here. Okay, therefore next is meet homomorphism. Next is meet homomorphism. Okay, when this function will be called meet homomorphism if f of x meet y. Sorry, meet I have to write. F of x meet y is equal to f of x meet f of y. Therefore, here meet operation is preserved. That's why it is meet homomorphism. And third is order homomorphism. If order is preserved, that is, if x precedes by y implies f of x precedes by f of y. Okay, therefore three different types of homomorphisms is defined. First is joint homomorphism if the mapping preserves joint. Second, meet homomorphism if the mapping preserves meet. Third, order homomorphism if the mapping preserves the order. Okay, and the mapping is called homomorphism if it is both join and meet homomorphism. Okay, a mapping is called homomorphism. Mapping F is called homomorphism. Homomorphism if it is both join and meet homomorphism. Okay, this is very similar to a concept in group theory we have studied now. Okay, suppose instead of group, let me go for ring. In ring we have two operations. Then the ring homomorphism will be true if both the operations are getting preserved. Here also we are having two operations defined, join and meet. Therefore the mapping is called homomorphism if it preserves both Join and meet. That is, it is both join and meet homomorphism. Now one may have a question, why there is no need to consider order homomorphism. Now here we are going to discuss that every join homomorphism will be order homomorphism, and every meet homomorphism will also be a order homomorphism. This we will write by a note. Therefore, according to this note, if join is there, order should be there. If meet is there, order should be there. Okay. Therefore, here I will write every join into bracket or meet homomorphism is an order homomorphism. Is an ordered homomorphism. Therefore, if it is join homomorphism, it has to be order homomorphism. If it is meet homomorphism, then it has to be order homomorphism. Therefore, while defining the homomorphism property, the condition was given that the homomorphism should be both join and meet, because along with this join or along with this meet, order homomorphism is going to occur. Let us check how that join homomorphism gives us the order homomorphism. Okay, let me check by considering let F be join homomorphism. Let F be join homomorphism. What is the meaning of join homomorphism? F of x join y is equal to f of x join f of y. Join operation is present. Now we want to check whether it is order homomorphism or not. What one has to check for order homomorphism? X precedes by y implies f of x precedes by f of y. Therefore, here let me assume or suppose x precedes by y. Suppose x precedes by y. But if x precedes by y, what is the value of x join y? In the properties we have seen this. If x precedes by y, what is the value of x join y? X precedes by y means according to Hasse diagram, this will be a situation. X precedes by y. Then what is the join of the two? X join y is y. And what is x meet y? X. Correct, na?
Yes, ma'am.
Therefore, what this above equation is giving me? Okay. Let us apply f on both the sides, taking f image on both the sides. Therefore, above equation becomes, what it become? F of, yes, f of x join y is equal to f of y. Correct. But what we have assumed, as f is join homomorphism, f of x join y is f of x join f of y is equal to f of y. See what kind of situation we have obtained. A join B is B. Therefore, what is the relation? A join B is B. We have proved already in the property that this is true if and only A precedes by B. This is the same situation, no? F of x join f of y is f of y. Therefore, may I write f of x precedes by f of y? Correct? Therefore, if f is join homomorphism, we have shown that x precedes by y implies f of x precedes by f of y. Therefore, f will be automatically order homomorphism. Therefore, f is order homomorphism. Let us check the same thing with meet homomorphism. Similarly, let f be meet homomorphism. Meet homomorphism means f preserves meet operation. That is, x meet y is equal to f of x meet f of y. Okay, now we are checking order homomorphism. Therefore, what I have to suppose? X precedes by y. Say, x precedes by y. But if x precedes by y, what is the value of x meet y? Same situation again. X precedes by y, that is y is successor of x, then the value of x meet y is
X.
yes, good, it is x. Now what we will do? We will take f equation both the sides. F of x meet y is f of x. But what is the value of f of x meet y according to meet homomorphism? This is f of x meet f of y is equal to f of Px. Therefore, according to this situation, again A meet B, we are getting A, correct? Which is implies and implied by A precedes by B. Therefore, what the situation we are getting? F of x precedes by f of y. Therefore, here it gives us x precedes by y implies f of x precedes by f of y. Hence, f is order homomorphism. F is order homomorphism. Okay, understood the definition? Okay, this is very similar to the previous definition of homomorphism itself. Under lattice structure, we have two different operations, join and meet. Therefore, homomorphism is defined separately for join, meet, also for order. Therefore, join homomorphism is F preserving join, meet homomorphism is F preserving meet, order homomorphism is F preserving the order also. And a mapping we call a homomorphism if it is both join and meet. We are not taking order because if the mapping is either join or meet, according to this node, it will be the order homomorphism. Is it okay? The next definition comes with isomorphism. Can anyone tell me a definition of isomorphism?
It is one onto one homomorphism.
It is not onto. Onto is not necessary for isomorphism. I think many times we have discussed this point. Okay. Therefore, this is one-on homomorphism. Onto is necessary if we want to prove the two algebraic structures to be isomorphic to one another. Okay.
Yes,
So
ma'am.
here a mapping, yeah, from L to M is said to be isomorphism. Is said to be isomorphism if F is 1 and homomorphism. Okay, now what this homomorphism includes? It includes join and meet homomorphism. Correct, na? Correct, na? It includes both join and meet homomorphism. This concept is very similar to a concept we have seen in the vector spaces also, no? L plus and dot. If this is my vector space, say V I will write. Then when we are saying this to be homomorphism or linear, if f of x plus y is f of x plus f of y. That is, it preserves addition. Similarly, we are writing for alpha x, alpha into f of x. Means it has to preserve both the operations. Here also, the lattice should preserve both join and meet homomorphism. Okay, let us go for an example to understand. Okay, we will write three lattices, L, M and N be the lattices. We will draw the Hasse diagram for all the three. This is L homomorphism. The vertices are A1, C1, D1 and B1. Second is M lattice having two elements, say A2, B2. This is M lattice. Third is having 4. A3, C3, D3 and B3 say. Okay, now the first example we will take is, first subbit I will take A. Here we are going to define, if we define F from L to M by, how I am going to define, say check f of A1 is equal to f of C1 is equal to f of D1 is equal to A2 and f of B1 is equal to B2. Is it a mapping first? If I am going to define like this, is it a mapping? Yes or no? Images of the three elements A1, C1, D1 is A2. We have defined. Means the three elements, these lower three elements are mapped to A2. That of this B1 is mapped to B2. This is the mapping we have defined. Now what one has to check? We have to check whether this is a homomorphism. To check it is a homomorphism or not, we have to check whether it is joint homomorphism, meet homomorphism. Okay, let me check. Now actually we have to check for every pair. Correct na? So for here I will make a start. I will check for A1 B1 pair first. Therefore I will write f of A1 meet. I will check A1 meet B1. What is A1 meet B1? What we have to check? It must be equal to f of A1 meet f of B1. We will find both the values and we will check whether these two are equal or not. What is A1 meet B1 here? Yes, can anyone answer me? What is A1 meet B1? Am I audible clearly?
Yes, ma'am.
Yes, ma'am.
Huh. What is A1 meet B1? Lower bound for this two.
A1.
A1. Good. Therefore, this is f of A1, na? A1 meet B1 is A1. But what is f of A1? What is f of A1?
F of C1.
Okay,
A2.
just give me a second.
Okay.
Okay, what is the value of f of A1? F of A1 is
A2.
A2. Correct now? Now f of A1 join f of B1 we want to find. What is f of A1? Defined it is A2. Join with what is f of B1? This is B2. Now we want to find out what is A2 meet B2. What is B2? What is A2 meet B2 then? A2 meet B2, that is the lower
A2.
bound. Yes, it is A2.
A2.
Means both the values are same. Therefore, what we have obtained? F of A1 meet B1 is equal to f of A1 meet f of B1. Likewise, how many pairs do we have? Many pairs are there, no? Actually, let us check for one more pair, A1 C1. Let me check A1 meet C1. F of A1 meet f of C1. Correct? Let us check the value. What is A1 meet C1? Lower bound.
A1.
A1. Okay. Therefore, here I will write A1 f of A1. But what is f of A1 defined? This is A2.
A2.
Correct. Now let us check what is f of A1. It is A2. Meet with what is f of C1? A2 again. And what is A2 meet A2? Always singleton check, right?
A2.
A2. Therefore, again these two are equal. Therefore, one can write f of A1 meet C1 is equal to f of A1 meet f of C1. Correct? Okay. Therefore, for this pair also meet homomorphism exists. What are the remaining pair? A1 C1, A1 B1. How many pairs we can check? A1 C1, A1 B1, A1 D1. Two we have checked, three are there actually. Right now, one may check similar. Therefore, here one can say that for all the pairs, meet homomorphism exists. Therefore, may I write? Similarly, it is true for other pairs. Similarly, it is true for other pair. Or should we check for A1 D1 also? You can check it, no doubt. Okay, similarly, it is true for other pair. Therefore, may I write F is meet homomorphism. F is meet homomorphism. Let me check whether F is, this is first, we have checked it is meet homomorphism. Let me check whether it is order homomorphism or not. Let us check if it is order homomorphism or not. What order homomorphism tells us? If A1 precedes by C1, the corresponding f of A1 must precede by f of C1. Correct na? Here A1 precedes by C1. Correct? What is f of A1 and f of C1 then? What is f of A1? A2. what is f of C1?
A2.
A2. Therefore, may I say A2 precedes by A2?
Yes.
Reflexive. Correct now?
Yes, ma'am.
Suppose I take another one. A1 precedes by B1. A1 precedes by B1. What is f of A1? A2. What is f of B1? B2. Whether A2 precedes by B2 or not. Whether A2 precedes by B2 or not.
Yes,
Yes.
ma'am.
Correct now? Therefore,
Yes.
here we can write f of A1 precedes by C1, which will imply f of A1 will precede by f of C1, and A1 precedes by B1 will imply f of A1 will precede by f of B1. Why this is so? Because f of A1 is A2 and f of B1 is B2, and A2 precedes by B2 holds. Therefore, I can write for similarly true for other pairs. If you want, you can check for all the pairs. Similarly true for other pairs. Therefore, may I say F is order homomorphism. F is order homomorphism. Now, third we will check whether F is joint homomorphism or not. Therefore, let us check F of C1 join D1, C1 join D1, and f of C1 join f of D1. We will check for this pair. What is C1 join D1 according to this
D1.
sketch? Yes, it is B1. Therefore, it will be f of B1. But what is f of B1 we have defined? It's B2. Correct, no? This is B2 we have defined. Let us check what is f of C1 and f of D1. Both C1 and D1 we have defined to be A2, A2. So this is A2 join A2. What is the value A2 join A2?
A2.
This is A2. Therefore, these two are not equal. F of C1 join D1 is not equal to f of C1 join f of D1. Therefore, one can say that F is not join homomorphism. Correct, na? What we have proved with this first example, whatever the mapping given to us here is neat homomorphism, is order homomorphism, but it is not joint homomorphism. Therefore, may I say F is not homomorphism. Correct, na? Hence, F is not homomorphism. Correct? I will give you another example with the same sketches. Okay, what we are going to define G, another mapping G from L to M by. How I am going to define is G of A1 is equal to A2, G of B1 is equal to G of C1 is equal to G of D1 is equal to G of B2. Okay, and the today's homework is to check whether this is joint homomorphism, meet homomorphism, and order homomorphism. Check, correct now? Can you do this? Similar process what we have discussed in the previous example, so that you can get the idea of homomorphism. Therefore, this
Ma'am,
example I keep. Yes.
मॅम तुम्ही म्हणलं ना जॉईन आणि मीट ऑर्डर होमोमॉर्फिझम इम्प्लाय करते मग ते नेसेसरी आहे का ऑर्डर होमोमॉर्फिझम दाखवण्याचं?
नाही प्रश्न नाही कळाला मला तुमचा. जॉईन आणि मीट इम्प्लाइज ऑर्डर.
हा मग ऑर्डर पण चेक करायचं का मॅम?
No, not necessary to check order. You can check only join and meet. म्हणजे इथं तुम्ही काय चेक करणार आता? जॉईन मीट जॉईन होमोमॉर्फिझम आहे का चेक करायचं, मीट होमोमॉर्फिझम आहे का चेक करायचं, सफिशियंट. मागच्या एक्झाम्पलला आपण ऑर्डर का चेक केली, कारण इथे जॉईन होत नव्हतं, मग मी 3 वेगवेगळे तुम्हाला करून दाखवले. ओके, आता या एक्झाम्पलला पण इथे मीट होमोमॉर्फिझम होत नाही.
ओके मॅम.
Giving you the answer. You can check order also. Here you check all. You check meet, you check join, and you check order also.
Okay, ma'am.
Okay. Now the next point of this topic is sublattices. Next point of this topic is sublattice. What is subgroup we have defined? Subspace, subgroup, subring. Because here the definition was parallel.
As a non-empty subset defined with the same operations on a group.
Hmm. Only defined with the same operations. Do you need any other extra condition? H is said to be a subgroup of G. Suppose G is having a binary operation star. Then what is the condition for H? Star
In
is defined, okay. Huh.
AB inverse belongs to that set H.
The inverse belongs to you are telling me that necessary and sufficient condition.
Yes.
Okay. Instead of this, may I say closed operation is essential. It
Yes,
should be
ma'am. Yes.
closed under that binary operation star. Na?
Yes.
For here also, a non-empty subset of a lattice is called sublattice if it is closed under both operations of join and meet. Both operations of join and meet. Let me write. A non-empty subset L dash of a lattice L is called a sublattice is called a sublattice of L if what if for any AB in L dash it implies A join B and A meet B are in L dash. Correct now? Therefore, what is the meaning of this statement? This is closed under join and meet. L dash is closed under join and meet. Let me write that is the algebraic structure L dash with join and meet is a sublattice if it is closed under join and meet. Okay, closed under the two operations join and meet. Okay, let me write some remarks on this definition of sublattice. What about a singleton set? You can say if I have a singleton subset of a given lattice, whether it will be a sublattice. Because for sublattice, what is the condition essential? It should be closed under join and meet. That is the only essential condition. But if I consider a singleton subset, whether it is closed, A join A is A, therefore it is closed under join. A meet A is A, therefore it is closed under meet as well. Therefore, may I say every singleton subset of lattice L are sublattices is sublattice. Correct, na? Is there any
Yes.
doubt with this?
No, ma'am.
See, suppose this is a singleton A subset of L. Correct, na? Singleton A. We want to check whether this closed. Now we have only one element, therefore we have to check for the same element. A join A is A. Similarly, A meet A is A, and both are in the corresponding singleton. That's why every singleton subset of lattice must be a sublattice. This may be a question for your objective, na? Every singleton subset lattice sublattice or not. Okay. Therefore, also one can write every sublattice is lattice. Every sublattice is lattice. Number 3 I can write is union of two sublattices. Union of two sublattices. Yes, what you can say whether it is sublattice or not? Hmm? What do you think? Union of two sublattices. What about union of two subgroups? Is it a subgroup always? Students? Okay, union of two sublattices may not be sublattice with the same reasoning, with the same reasoning for the group. Correct? Now we will go for next point of the syllabus, that is special lattices. Okay, under special lattices, we are going to study different lattices such as modular lattice, complemented lattice, bounded lattice, etc. and etc. But before going to that, I think the first lattice we are going to study is complete lattice. Therefore, to understand complete lattice, what we are going to do, we are going to make the generalization of existence of LUB and GLB for any finite subset of a given lattice. Okay. Let me write a heading, special lattices. What we have defined in lattice? Lattice, algebraic structure is said to be a poset is said to be a lattice if every pair of elements extend this for the 3 element subset, for 4 element subset, for finite and for infinite. That is what a question is. Okay. Now here let me write that in lattice every pair of elements has LUB and GLB. Whenever we are writing every pair of elements, means it is a subset with 2 elements. And now as a consequence of this fact, we can show using the principle of mathematical induction that the every subset has LUB and GLB, rather finite I will call. Okay. Therefore, for n equal to 2, that is, okay, first I'll write as a consequence of this fact, one can show by using principle of mathematical induction that every finite subset of lattice has LUB and GLB. Okay, see, check now. For if I say n to be the number of elements, then all the singleton sets are having LUB and GLB. That is, the result is true for n equal to 1. Correct now? And we are saying the for every pair of elements LUB GLB exists. To 2 also the result is true. Now let us check for n equal to 3. Let us check for n equal to 3. That is 3-element subset of lattice. 3-element subset of lattice. Correct now? What are the 3-element subset? Let me take the 3 elements as suppose A1, A2, A3 of L. Whether LUB and GLB exist for this 3-element subset of a given lattice or not. Okay. Now if A1, A2, A3 belongs to L, what about A1 join A2 is in L? No doubt, because for every 2-element subset join exists. Now let me take this as one element and take a join of this element with A3. Therefore, what is the value? A1 join A2 join with A3 must be an element of L. Okay. Now one has to check whether this will be LUB for A1, A2, A3. Okay. Okay. To check whether it is LUB or not, first we have to check whether it is upper bound for A1, A2, A3. Therefore, to check this, I will write, we know A1, A2 both precedes by A1 join A2. Okay. And A1 join A2 will precede by A1 join A2 join A3. Therefore, I can say that A1 join A2 join with A3 is upper bound of A1 join A2 and A3 as well. Here I can write A3 also precedes by A1 join A2 join A3. Therefore, from this 1 and 2, check. A1 join A2 precedes by this. A3 also precedes by this. Therefore, one can say A1 join A2 join with A3 is upper bound of A1 join A2 and A3. Right now. So we have proved this is an upper bound. Now to check this is the least upper bound, what we will do? We will take an arbitrary upper bound of A1 join A2 and A3 and we will show this quantity is the least one. Okay. Yeah, I will write to show A1 join A2 join A3 is LUB of A1 join A2 and A3. Let C be arbitrary upper bound of A1 join A2 and A3. Correct na? If it is an arbitrary upper bound, what I can write? A1 join A2 and A3 both will precedes by C. Correct na? If both will precedes by C, what about the join operation among the two? C is an arbitrary upper bound. Correct. Therefore, may I write to the next step? A1 join A2 join A3 will also precede by C. You have to understand this X and Y precedes by A say, then X join Y will also precede by A because A is the arbitrary upper bound. This is arbitrary upper bound and join is least upper bound. The same fact here we have used. Therefore, A1 join A2 join A3 is least upper bound of A1 join A2 and A3. Okay. Therefore, here one can say that is how many ways there are there to write? A1 join A2 join A3 or A1 join A2 join A3 or many ways one can write. Therefore, combinedly I can write this is join of AI. I runs from 1 to 3. Therefore, LUB of 3-element subset exists. LUB of 3-element subset exists. With a similar reasoning, one can say that GLB of a 3-element subset will also exist and it was given by the meet of the 3 equals to 1 to 3. That's what we have shown that for every 3-element subset also LUB and GLB exist. Therefore, in general, one can say for finite subset S, okay, here I will write thus LUB and GLB of 3-element subset exist. Therefore, continuing this, one can say that it is true for every finite subset. Therefore, in general, for any finite subset, S of L. See, I am saying finite subset, okay? And finite number of elements. Subset S of L. Suppose S is having some n number of elements, A1 to AN. The LUB and GLB exist, okay, and as exist as how it is LUB of the set S is join AI I equals to 1 to N, and what is GLB of the set S? GLB of the set is meet AI I equals to 1 to Yes. Therefore, for every finite subset S of the lattice, the GLB, LUB exists. But here one can check that for this may not exist. Therefore, here I will write a remark. The lattice may fail. The lattice may fail to possess LUB and GLB for arbitrary subset. See, whenever I am saying arbitrary subset, it may include infinite subset. Okay, that is may there may not be LUB and GLB of an infinite subset. We cannot have a guarantee about the infinite subset of lattice. We have given a guarantee about the existence of LUB and GLB only for the finite set. If I want to give an example, suppose Z plus with less equal. This is a lattice. Whether it has the LUB, no LUB. Okay, is this point clear to everyone, or is there any doubt on this? Hmm? Yes, we do not have a guarantee. Here I have given the examples also. Okay, therefore, if this point is understood, let us define the first special lattice called as complete lattice. The first special lattice we are going to define is complete lattice. Definition is quite easy. Definition says that a lattice is called complete if each of its non-empty subset has LUB and GLB. Okay, I will write a lattice is called complete if each of its non-empty subset. Now this non-empty subset may be finite, may be infinite. Okay, each of its non-empty subsets has GLB and LUB. Correct? Okay, this is the first special lattice we have defined called as complete lattice. Okay, the lattice is called complete if each non-empty subset has LUBs and GLBs. Let us have a look on the example. The first example one can tell is finite lattice. Because for finite lattice, there is no question to have the infinite subset. Therefore, finite lattice is always a complete lattice. A finite lattice, I will write every finite lattice. Every finite lattice is complete. How many finite lattice examples we have seen? Every finite lattice is complete. Correct now. Let me, if I want to give an example, this is an example, say lattice L with defined as a power set under union and intersection as join and meet. And if I take suppose S is equals to 3 element subset ABC. S is a 3 element subset ABC. How many elements this power set will take? Yes. How many elements this power set will take?
8 elements.
8 elements. 5 singleton A, singleton B, singleton C, singleton sorry doubleton AB, doubleton BC, doubleton AC, and the set itself A, B, and C. Now you may check now for every finite subset you take any finite subset. Okay, if I take any finite subset, whether the GLB is going to exist or not. According to this discussion, for every finite subset, LUB, GLB is going to exist. Therefore, this is also an example of a complete lattice. This is also an example of a complete lattice. Every finite will be complete. Okay, any doubt with this? Okay, next point we will study universal bounds. Universal bounds. Okay, now universal bounds is defined with the help of a complete lattice. Okay, for every complete lattice, it will have least and greatest element. Correct, na? Whenever we are saying complete lattice, it should have a least element and greatest element, and those least and greatest elements are called as bounds or units or universal bounds, and the symbol we will use is 0 and 1. Okay, here I will write every complete lattice have least and greatest element. I think you have studied already what is least and greatest element. Correct, na? Kohli sir has taught you this. Therefore, the least and greatest element, the least and greatest element of lattice are called bounds or units or universal bounds. Universal bounds of a lattice, and we are going to denote it by 0 and 1. Denoted by 0 and 1 respectively. That is, least element is denoted by 0 and greatest element is denoted by 1. Okay, least is 0, greatest is 1. Okay, next definition is bounded lattice. The definition itself tells you a meaning. A lattice which has both universal bounds, that is 0 and 1. That is the least element and greatest element is going to exist. Okay, let us write the definition. A lattice, L, join, meet. Okay, I will write the definition first. A lattice which has both elements 0 and 1 is called bounded lattice. And is denoted by L, join, meet along with 0 and 1. So that these two will denote the existence of the least and greatest elements, universal bounds. Okay, let us write some remarks on this. The first remark is every finite lattice is bounded. Okay, because we have seen every finite is complete, and for complete 0 and 1 is going to exist. Right? Therefore, the first example is every finite lattice is bounded. There may be the question for objective on this relation. Every finite is complete is bounded, therefore every finite is bounded. Okay, therefore this is the first, every finite lattice is bounded. Suppose I want to give an example for power set with union and intersection. This is a bounded lattice again because it is finite. What is the bounds? What is the least element? And what is the greatest element? For the power set, what is the least element? The element situated at the bottom in the Hasse diagram. What is that element?
5.
5. Good. And the greatest element is situated
ABC.
at the top.
ABC.
That is the set itself. Here we are not differentiating. Correct na? Therefore 0 is 5, 1 is yes. Okay. Next, Z plus with divisibility is not bounded. Z plus with divisibility is not bounded because you do not have a greatest element. Correct na? Yes or no? Z plus is the set under consideration and divisibility is the order relation, is the relation, partial order relation we are defining. Then what is the least element? Hmm. If I want to draw an Hasse diagram, is it possible? What is the
One.
element at the, yes, the least element is 1. Least element exists. Least element is 1. But what is the greatest element?
Not exist, ma'am.
Not, no greatest element. No greatest element. Therefore, this is not bounded. Okay. Instead of z, if I make, instead of z plus, if I make z only under the same divisibility relation, whether it is bounded?
No, ma'am.
No, it is not bounded because you don't have any least and no greatest of it. Correct? Not bounded. Is it clear to everyone? Okay. One more property was written here. For any arbitrary a in L, if 0 and 1 are universal bounds, 0 and 1 are universal bounds, then what is the value of a meet 0 or 0 meet a? Hmm? A is arbitrary element of the set. 0 and 1 are the universal bounds. That is, this is my least element situated at the bottom, and this is the greatest element situated at the top of the Hasse diagram. Then what is A meet 0, 0 meet A?
0.
0, good. What is join? A join 0, 0 join A?
A.
Yes, it is A. What is 1 meet A? A meet 1?
A.
A.
A, good. 1 join A? A join
Again 1.
1? Yes, it is 1. Okay. These may be the questions for your objective, remember. Okay. Next, we will go for the third special lattice called as complemented lattice. Before that, we will see what is complement of element in lattice. Complement of an element in the lattice. Okay, what is the complement we have studied previously? Hmm? In power set relation, we have studied complement, na set, complement of a set. What is the complement of a set A in the universal set U? This is U minus A, na? Correct, na?
Yes,
Yes,
ma'am.
ma'am. Yes.
Suppose this is my universal set A. Yes, I will change the color of my pen. Suppose this S is the universal set and A be a subset. Okay. Then what about A complement? A complement we are defining as S minus A. Then B is said to be a complement if A union B is yes, na? And A intersection B is 5. Correct, na? कॉम्प्लिमेंट कसा डिफाइन केला सेटचा आपण हा कॉम्प्लिमेंट कसा होईल ए एंड बी इज अ कॉम्प्लिमेंट टू वन अदर तर दोन्ही मिळून एस व्हायला पाहिजे युनियन आणि इंटरसेक्शन इन द बाउंडेड लॅटिस ओनली वी हॅव लीस्ट अँड ग्रेटेस्ट एलिमेंट इन अ बाउंडेड लॅटिस एल जॉइन मी 0 1 an element B in L is called is called complement of A is called complement of A in L if what if A join B is 1 and A meet B is 0. A join B is 1 and A meet B is 0. Okay, any doubt with this? We will write some remark on this complementary lattice. I will tell you that with an example also, no doubt. Okay, the definition of complement matrix is symmetry. The definition of complement is symmetry. Why it is symmetry? Because if in this situation I am saying B is the complement of A, can I say A is the complement of B? Correct, na? Therefore, this definition is symmetry. Okay. Second one is element may or may not have complement. It belongs to M. May or may not have complement. Existence of complement is not sure. Okay. Next, complement is not unique. Complement is not unique. But only for the bounds 0 and 1 are unique complements of one another. 0 and 1 are unique complements of one another. Okay, to understand the example, by the example, let me define a complemented lattice first. Complemented lattice. What is complemented lattice? Again, the name itself is. If every element has a complement, then it is complemented lattice. A lattice L is called complemented lattice is called complemented lattice if it is bounded and if every element in L has complement. Why boundedness is essential? Because for the existence of complement of an element, we need a bounded lattice. Therefore, complemented lattice must be bounded so that least and greatest element exists. And if every element of the given lattice has a complement, then it is the complemented lattice. First example we will check. Suppose this is the Hasse diagram of a lattice given to us. These are least and greatest element, and these are my two elements, say A1, A2. We will check whether the complement of every element exists or not. We know for least and greatest element, no need to check. These two are unique complements of one another. Why? Because 0 meet 1 with 0, 0 join 1 is 1. Therefore, 0 and 1 are the complements of one another, rather unique complements of one another. What is the complement of A1? What is the complement of A1? To find the complement of A1, we want to find out one element such that A1 meet X is 0 and A1 join X is 1. We have to find such a X. Okay. Now how many elements do we have? Let us check with 0. If I check with 0, A1 meet 0 is 0, but A1 join 0 is A1. Second condition fail. Therefore, let us check it with A2. What is A1 meet A2? Yes, from the 0 now. What is A1 join A2? 1. Therefore, complement of A1 is A2. Complement of A1 is A2. Here we found unique complement. Let us take another example. Students, are you there or not?
Yes,
Yes,
ma'am.
ma'am.
Okay. Let me take one more. I will take this example and I will stop. This is say A1. This is say A2. This is the greatest element. Somewhere here it is A3, and this is my least element. Okay. No doubt to check again for least and greatest element, they are the unique complements of one another. What is the complement of A1? What do you think? What will be a complement of A1? We want to find one element such that A1 meet with that element is 0, join with that element is 1. Therefore, here we can observe if I take A1 join with A3, it is 1. Na? A1 join with A3 is 1. What about A1 meet with A3? 0. Therefore, complement of A1 is A3. Since A3 is 1, A1 meet A3 is 0. Okay. What is complement of A2? What is the complement of A2? On the parallel lines, may I say A2 join A3 is 0. What about A2 meet A3 is 1? Correct, na? Therefore, here the complement of A2 is A3. Let me find out the complement of A3. Now here, from this previous two, complement of A1 is A3. Therefore, complement of A3 is A1. Complement of A3 is A2. Therefore, I can write complement of A3 are 2, A1 and A2. That's why here we have written a complement is not unique. Right? Therefore, this is an example actually. Therefore, if in every lattice, if every element has a complement, then it should be a complemented lattice. Okay. In the next lecture, we will go for modular lattice and the rest part. We will stop for today. If you have any, okay, this is what for today's lecture. Students, if you are having any difficulties about today's lecture, because some 3-4 definitions we have studied regarding the lattice today. If you have a difficulty, you can ask me. Unmute yourself and ask. Okay, if not, thank you for watching the lecture.